All right. So, things we got going on this week, besides it being the last week of class, is today and Wednesday we're going to Chapter 11. Friday, we won't get through all Chapter 11, but that's okay, because we pick up with Chapter 11 and 109. So, your final mastering is on Wednesday. It covers Chapter 11 stuff. Friday in class we'll do final exam review day. There's already a practice test on my website, so you can start looking at that if that's helpful. Jumping down number 4, the study guide. If you still want one, it's on sale. We're the same place you got your goggles. You can split one with someone else. You can borrow someone else's, whatever you want. And finally, course evaluations. You've probably gotten a million emails reminding you to do your course evaluations. Let me remind you how critical they are. One, it's the only way you can tell me anonymously what you liked or what you hated about the class. One, I don't know who writes what. And 2, I don't even get them until next semester. So by that point, you're already gone. So I can't really figure out who wrote what. So if there's things you liked, like, man, I really liked you videotaping the lectures, keep doing that. Or if I really liked mastering, I really hated mastering. I wish there was less homework. I wish there was more homework. I've never gotten that one. I wish we didn't have quizzes at all. Or whatever it is. The only way I know to fix it is if you tell me. And the same thing goes for any course, right? All the course evaluations, the only feedback the professor gets is from these course evaluations. And the only way, if you really appreciate a professor and what they do, the only way their chair, their dean, and the president knows that is if you say so when you're doing evaluations. If you think there's some areas for improvement for a professor, same thing goes. The only way the professor knows, their chair knows, the dean knows, the president knows, is if you tell them. And so if you think there's some things the professor is doing awesome, or some things that they could be doing better, the only way they know is if you tell them. And so my incentive to fill out your course evaluations, if by this time, 1 o'clock on Friday, if you guys have reached 90% or better response rates, I'll bring in something, cookies or donuts or something delicious.
Or automatic 10 on a
Oh, you already did all your bonus points. No, I can't do that anymore. Yeah, it turns out I can't do anything about grades in relation to course evaluations. That's considered unfair. But I can bring in delicious snacks. So, if we get to 90% or better, I'll bring in something. All right. Questions about any of that? Okay. In that case, let's do a little Chapter 11, Intermolecular Forces. So a lot of this is going to pull in the stuff we did in Chapter 7, 8, 9, 10 about Lewis dot structures and polarity, and combine it with the stuff we now know about molarity and intermolecular forces, and it's just going to kind of wrap things up, hopefully. All right, so, right, there's these 3 states of matter. We got our gases, our liquids, and our solids. Right, so gases have any volume and shape, whatever the container is. They have low density comparatively. They are very free in motion, just like we saw in the kinetic molecular theory of gases, right, that they're able to move around a lot. That's different than liquids and solids, right? So liquids have less ability to move around. Solids have even less, which means they have higher density. So the density is directly related to the motion of the molecules, or the freedom. So the more motion, the lower the density. The less ability they have to move around, the higher the density. So the question is, why is that, and how do we overcome that? So the closer the molecules, the greater effect intermolecular forces have. All right, so the closer they are, the more they affect each other. Let's say I have an ice cube and I want to turn it into water. What is the easiest way for me to do that? Add heat, right? If I want to go from a solid to a liquid, I have to add heat of some way. Or if I want to go from a liquid to a gas, the easiest way to do that is to heat it. So addition of thermal energy can overcome these intermolecular attractions. So they don't disappear, but I can add enough energy to push them apart. Which is what we saw, right, when we did thermodynamics, that I can add something and force it to change states of matter. And it's just a different type of energy. So, when I'm talking about additional thermal energy and changing states of matter, how exactly does that work? So, using temperature, which I just said, or pressure, we can convert from one phase into another. Is that a physical or chemical change if I'm changing states of matter? It's a physical change. So all I'm going to do is do a physical change, one phase to another phase. That's just a review question. Excellent. Good. So here I have my solid. Then I got my liquid. Over here I have my gas. And if I wanted to go solid to liquid, an easy way for me to do that is to add heat. And if I want to go from my liquid to a gas, right, I could add some more heat. And I could reverse that. I could go from steam back to water, and I can go from water to an ice cube. All right, those are the ones that come to mind first, like heated up, cooled off. We could also change the pressure. So, if this liquid is at 2 atmospheres, right, and I decrease the pressure by half, I've now I've put less pressure on it, so now the molecules have more ability to move around. That one's hard to think about. Let's go the other way. If I have gas that's at 1 atmosphere, right, room temperature gas, and I increase the pressure, so I squish down hard on it, I'm going to force it to go from a gas to a liquid. All right, so if I increase the pressure, I'll make it into a liquid because I've given it less space to move around in. So it may be easier to think about this in terms of something you see all the time. I don't know if you see it all the time. You've at least been around. Ignore my terrible artwork. All right, so this is my propane tank. Right, that kind of looks like a propane tank, sort of. Anyone do a deep fried Thanksgiving turkey with your propane tanks? All right, so here I have my liquid propane. Right, you know it's a liquid because when you move the tank around, you can hear liquid sloshing around in there. And so it's liquid because it's under high pressure. All right, so under high pressure, it's now a liquid. If you release the valve, what happens to the pressure? Do I put more, right, it reduces the pressure, right? So I've opened it up to the atmosphere. It's going to reduce the pressure, so some of this liquid is now a gas. All right, this is where my artwork falls down. This is, right, your barbecue with wheels, right? I don't own one, so maybe they look like this. I don't know. Right? That's the lid. And here's or I'll put a dial on there. There, dials. Whatever you want to draw that looks like that. Look, and it's hot. It has flames. Hot. You should probably turn it down. That's probably too hot. The flames shooting out the top of the grill. Too much. All right, so now I'm under low pressure. So now it's a gas coming across to here. Because you can light the gas on fire, right? Because you don't, when you turn on your propane grill, you don't see liquid shooting out the top of the burners. You shouldn't. If you do, immediately turn it off. You have a serious issue. You should hear it. You should hear some gas coming through, and then you light the gas. And so this propane tank is under high pressure, so it keeps it as a liquid. And then when you open it, it becomes a gas, and then you can light the gas. And you have delicious food to eat, in theory.
What keeps the gas back at the tank from catching on fire?
Oh, it is usually a release valve at the barbecue end that regulates how much gas is actually getting through. It keeps the flame from like getting sucked backwards. Because if you had a pressure issue where this was under, if this was pressurized incorrectly, yeah, in theory it could suck the flames backwards. But there should be enough valves on your propane tank and barbecue that are working correctly to keep it from getting sucked in. So, but yeah, as you burn it though, you use up all the gas and it sucks more liquid this way because you use up the gas, so it keeps getting sucked this way. So, which we'll talk about in 1 and 9, talking about Le Chatelier's forcing reactions one way instead of the other, but that's a preview. That's for free, preview. Questions about this? Next time we run the propane tank, be like, I know how this is working. Look at that. Next time the guy at the 7, do you guys have 7-Elevens here? No. Whatever Quickie Mart you go to and get your propane tank. You can be like, hey, guy selling me the propane tank, do you know how this works? Okay, maybe don't do that. All right, so what is going on between atoms in your propane that keeps them as a liquid versus a gas versus a solid? It's all due to intermolecular forces. So, intermolecular forces originate from interactions between charges, right? These would be things like ions, right? Full-on charges, versus partial charges, which would be things that are polar, versus temporary charges, which are things that are non-polar. Now the thing to think about is when I have an intermolecular force, that is something that is between two molecules separated in space. That is different than a right, a covalent bond is between two atoms within the same molecule. So if we're talking distance-wise, intermolecular forces have to be farther apart, right, than covalent bonds, because this is in the same molecule. These are two different molecules. So intermolecular forces are weaker because of distances involved. So if we think about it, let's say I have water. If you're doing the slides, this is on the next slide. I just decided I skipped their pictures on, it gave it away, so I decided to just draw it. All right, so here's my liquid water. Right, there's liquid water hanging out. Right, now I have two liquid waters, which means I now have some intermolecular forces going on. All right, so what is this stick representing? A covalent bond. How many electrons? Two, right? There's two electrons. It means there's two electrons hanging out between the oxygen and the hydrogen. And for that to happen, they have to be pretty close to each other for the electrons to be sometimes around over this side. So typically, a bond is around 96 picometers-ish. So scale-wise, your hair is about maybe 10 nanometers. This is 1,000 times smaller than that. So if you took your hair, sliced up to 1,000 pieces, one would be this distance-ish, depending on your hair and whatnot. All right, so pretty close, right? Pretty close in space. These guys, this oxygen to this hydrogen, this intermolecular force is between like 300 picometers. So still small, but 300 times farther away than this bond. All right, so if this is about 100 picometers, this is 300 picometers, so much, much farther away. And because it's much farther away, the interaction's weaker, right? They just can't get as close.
Is it just from the other molecule or from like the oxygen to the hydrogen?
I mean, it's going to be the oxygen to hydrogen. Yeah. Because really, we'll get to why. But yeah, oxygen to hydrogen. All right, so 300 picometers to do that. So if the intermolecular force is the weaker one, if I add thermal heat, which one should break first? Break this one or break this one? Intermolecular or covalent? If I add heat. We're going to break this one. Intermolecular is weaker, so I'm going to break that one first. All right, so if intermolecular is weaker and it breaks first, if this is liquid water, and I add thermal heat to force them apart, what have I made? I've made steam, right? So I added thermal energy. I forced these molecules farther apart. They were a liquid. Now it's a gas. What temperature does that occur at? Water to gas for water. 100, right? 100.
The intermolecular one was 300, right?
Yes. All right, so if I go liquid water to gas water, I need 100 degrees Celsius to push these two molecules farther than 300 picometers apart. Which you do all the time. You just now know what's going on. Do you think I need more or less thermal energy to force the hydrogen to leave the oxygen? More, right? Because this is stronger. So if I want to break this, I need to get all the way up to 1,000 degrees Celsius to break this bond. Right, a lot more. Much closer, much stronger. So it needs more thermal energy. Questions on that? All the kind of stuff you've thought about, but maybe not the chemistry why. All right, so intermolecular forces fall into four big categories. The first one is dispersion forces. So this is an intermolecular force present in all molecules and all atoms. Forgot the ion is. So this force is a result of fluctuations in electron distribution around the molecule. All right, so let's say I have this guy. All right, so I have methane. Is methane polar or nonpolar? It is nonpolar, right? Because it's all evenly distributed. So if it's nonpolar, it means it has no poles, right? No poles. So we would assume that all the electrons are evenly split between a carbon and a hydrogen, right? There's two in there, and they must be just kind of hanging out, dead center in the middle, not closer to one guy or the other. Until you remember that electrons can't be pinned down like that, right? Because I've forced them to be in here, they're now no longer going to be in there. They're going to be wherever they want to be. In general, they're going to be somewhere between the carbon and the hydrogen, but not necessarily straight in the middle. So at any one instant, the electrons in a bond may be unevenly distributed. Right? So it may be, oh, my thing's crazy. So we like to think about the electrons being just between these two guys, right? Between the carbon and hydrogen, evenly split, somewhere in the middle. But at any one time, the electrons may be closer to the hydrogen than the carbon, or closer to the carbon than the hydrogen. And when they do that, it makes an instantaneous pole.
What?
Pole, instantaneous pole. Right, at any one given time, it may be that all the electrons are in the center, not near the hydrogens. But just for an instant. And then after that instant is gone, it'll go back to being nonpolar. So an instantaneous dipole, real quick. Right, makes a quick set of poles and then it goes back. Or sometimes it's called a temporary dipole. Well, I mean, it's the same thing. But let's say I have this temporary instantaneous molecule that looks like this sitting next to this one that doesn't have any poles. It's going to domino effect. All of a sudden, this H is positive. Just for an instant, it's going to make this hydrogen negative. Or it's going to try and pull some other one electrons to it. Well, now that H is positive, or negative. Now this carbon will be the opposite, right? This is negative, this is now positive. Well, that's positive, now this is negative. Like it's going to just a chain reaction of all instantaneous dipoles, and then the electrons will go back to normal. So it's just a quick flicker of poles, and then it's all gone.
So if that's a gas, what would that make happen to gas? Would you always make combustion?
No, it's happening all the time. It's just a little flicker of polarity, and it's gone. And even a flicker is too strong of a word. Whatever is faster than a flicker is how long they exist for. So it causes a domino effect and induces other temporary dipoles. So all molecules can do this regardless of it's polar or not polar. So all nonpolar molecules can do this. All polar molecules can do this. All ions can do this. You name a molecule, it's doing this dispersion force. So how do we know the likelihood of a molecule to start the domino effect? It comes down to a molecule's ability to polarize. So magnitude dispersion force depends on how easily we can polarize the molecule. So that comes down to its polarizability. That's a great Scrabble word. Right? If you had polar and you slapped down an I and a Z and an able, polarizable, that'd be good too. All kinds of triple word scores going on there. All right, polarizability. How easily can you distort the even electron distribution around a nonpolar molecule? All right, so before we had this guy. So how easily can I get the electrons from the hydrogen over to the carbon? Right, how easy is that? Well, polarizability it is more easy to polarize something the greater the molar mass. That also is a greater number of electrons. So the more electrons, the easier it is to distort the electron distribution around a bond. So, looking at my table, which one has the heaviest molar mass, the top or the bottom? Bottom, right? So this way we're molar mass. So increasing molar mass, going from CH4 down to CI. Which requires the greatest amount of thermal energy to get it to go from a solid to a liquid? It is not the negative. Right, so this is where it's confused. Let me draw a quick number line. Yes, the highest temperature. So if I'm down here at minus 200. So let's say all the molecules start off at minus 200. I only have to go to negative 182 to get this one to turn to a liquid. I have to go to 150 to get that. I got to go to negative 23. Oh, now I have to go past 0. Now I'm at 90. Now I'm at 171. So it requires the greatest amount of thermal energy to get the carbon tetride, whatever, CI4, to turn into a liquid, which means it has the strongest intermolecular forces. Right? It means I have to put the most energy into it to get two CI4s to push apart. So if it has the most energy required, it means it is the it has greater polarizability compared to these other ones. That's more likely to be pretty much polar compared to CH4.
The most energy required for strong.
Yeah, so 2 different points, sorry. Most energy required, which then means it has the strongest intermolecular force, which means it is most like a polar molecule. You guys look super fascinated. Just wait. There's more to come.
So that one has the highest polarizability.
Yes.
Okay.
Yeah. It is most like a polar molecule. All right. So we can then take this similar argument and apply it to things that are actually polar. So molecules that are permanently polar all the time will have dipoles. So existing all molecules are polar, where polar molecules are ones that have permanent dipoles. Interchangeable. All right, so if I look at, for example, let's do all right, so I have these 2 molecules. First question is this molecule polar or nonpolar? It is polar. Is this molecule polar or nonpolar? It is nonpolar. All right, so can this guy have dipole-dipole forces? No, by definition it cannot. Can it have dispersion forces? Yes. Can this guy have dipole-dipole forces? Can it have dispersion? Yes. Which one of these 2 then should have the higher boiling point? Polar or nonpolar? The polar, right? It has more forces, so it requires more energy to break it apart into a gas or a liquid. So this one, I only need to go to minus 88. This has to go all the way up to minus 19.5. It has a higher boiling point because there's greater intermolecular forces. It's being held together not just by dispersion forces, but by dipole-dipole forces. Questions about that? All right, in that case, let's talk about how dipole forces work with miscibility. Then we'll talk about a very special type of dipole-dipole. All right, so polarity is an important consideration when we're determining miscibility. All right, so miscibility is the ability to mix into a homogeneous solution. So if I'm talking homogeneous, does it look the same all the way through, or can you see distinct layers? Looks the same, right? So polarity is important I want to make a solution that contains two different types of molecules that intermix with each other. What's our go-to example of two types of molecules that don't mix? Oil and water, right? So oil would be something like the one we just had. Right, we said that was nonpolar. And then we have water. So what kind of forces does my nonpolar molecule interact with another one with? It's nonpolar. Only has one kind. Dispersion, right? This only has dispersion forces and wants to hang out with other dispersion-only force molecules. Polar molecules want to hang out with other polar molecules. They want to have this dipole-dipole interaction that's much stronger. And so it sounds very, very segregation-y. Nonpolars only want to hang out with other nonpolars. And polars only want to hang out with other polars. They don't want to interact with each other. So I can have nonpolars with other nonpolars. So I could put this guy with, what's an example of another nonpolar I can think of? I'm drawing a blank. What else do I have? Right, those could be fine. Those are both nonpolar. They can hang out. That's cool. But water wants to hang out with other polar things, so it would hang out with something like, I'm trying to think of something polar. That'd be fine. Those two guys can hang out. Those are both polar. These are both nonpolar. So I can't mix these two categories together. It's just either this or that. All right, so the last thing I'm going to talk about today is the most important type of dipole-dipole force out there. So hydrogen bonding, or H bonding, is a subcategory of dipole-dipole interactions. So there's a special dipole-dipole interaction between a hydrogen atom attached to a nitrogen or oxygen or fluorine and a different atom that has an oxygen, nitrogen, or fluorine. The definitions make a lot of sense. We'll draw a picture. So if I have this interacting with all right, so I have ammonia interacting with water. Both of these are polar, right? Ammonia's polar, water's polar. I have now a hydrogen attached to a nitrogen, this guy right here, and an electronegative oxygen, nitrogen, and fluorine of an oxygen right here. I can also do the other two, right? I could have this guy interacting with that one. This nitrogen with that hydrogen. That would be fine. Looking at my squares, this H and this O, which of those two atoms is more electronegative? Oxygen or hydrogen? More electronegative. Oxygen is more electronegative, so does it want electrons or it wants to give electrons away? It wants them, so it's going to pull this hydrogen towards it. It wants that hydrogen electron. It's going to pull it towards it. Which is more electronegative, nitrogen or hydrogen? Nitrogen. So it's going to pull this hydrogen towards it. So it's stronger than just a dipole-dipole force. They are actually so electronegative that they are actually able to pull other molecules to itself. So the large electronegativity difference between the hydrogen on one molecule and the nitrogen, oxygen, or fluorine on the other molecule makes this hydrogen very much partial positive, and this one partial positive, which then gets sucked in towards these partial negatives. So, why is this so fascinating? Good question. I'm glad you guys asked it. It's the reason why life exists here on the planet Earth and nowhere else, because we have water. And water has an amazing ability to hydrogen bond. You have a question, Morgan, first? Before I got into a crazy tangent.
What is that positive negative thing?
What is it? I mean, what letter is that?
Or what is it?
Oh, we used it before when we talked about dipoles.
What you're saying that
It's, right. It becomes a little bit positive, but a very little bit positive. Right. So they're not full-on charges, not like an ion that has a plus. This is more plus than minus.
Okay.
Right, because when we use, like, oh, let me put it up here. If, right, back in thermodynamics we had big triangle, and that means big change. That's capital delta. Lowercase delta is this guy. Little change. Yeah, so it's just, you know, am I using my fancy Greek alphabet, throwing out some letters. So this means little change. So, back to fascinating facts about water. So, if we look at my table, we'll look at just this part. And we'll look at the whole thing. All right, so this is boiling points on this side. This is period, so going down. Let's look at this group 4A first, right? So I'm looking at carbon, silicon, germanium, tin, right? All in the carbon column, going straight down. Carbon, silicon, germanium, tin, right? I'm increasing my molar mass, going this way. And the boiling points increase, right? It takes more energy to make this tin tetrahydroxide turn into a gas compared to this one, right? These are all nonpolar. These are just dispersion forces. Fair enough. Let's look at these guys. I got the halogens, right? Iodine, bromine, chlorine, fluorine. Fluorine is one of our fantastic fancy molecules. So if I was looking at these guys, I would expect, right, HI is polar, right? It should have more energy to require it to get to boil compared to HCl. And it does, right? These three kind of do in a line. This, that, that. But then, whoa, what's over here with HF? It's the lightest. It should require the least energy to turn into a gas. Way wrong. It requires way more energy than HI. It's because these hydrogen bonds are super, super strong and requires way more energy than expected to push them apart. All right, we can do the same thing looking at oxygen's column, right? We got tellurium, selenium, sulfur, oxygen, those four.
Again, tellurium,
Should be, it is the heaviest. It should require the most energy to get turned to a gas. Not even close. It boils at minus 20. Water boils at plus 100. It should be, right, if I follow this trend line, it should be down here. And it's not. It's
it's nowhere close. It's
probably double, triple what it should be. The hydrogen bonds are so strong, right? Water requires a lot of energy to boil. Great for us, right? Our oceans are able to stay as a liquid. Your body is able to stay. Your blood's not constantly turning to a gas. You're able to maintain your temperature. The fact that water is able to contain so much heat, right, a specific heat, is pretty high, which means you can use it to cook food and not scorch food. It's just fascinating. I could talk about water for a week, which I do in biochem. We talk about a whole week worth of water, fun facts, but I will just keep it to, that was only 5 minutes. I could go on and on and on. But water, fascinating. Okay, I'll stop there because you guys look amazed. We are going to finish most of chapter 11 next week. We may not get through all of next week, next class. And then we'll do some review. If you did not pick up your exam,